Hey, good afternoon. All right. Any questions from last time? All right. Well, let's talk about the homework then. So, I posted your final homework assignment. And this is due a week from today, and it's a double point homework because it's kind of picking up homework 8 as well. So, a set of questions on counting and a set of questions on languages and automata theory. So the languages and automata theory we're going through today, but let me just run through the counting questions. And you've got to show your work on these. If you just write down an answer and the answer is correct, you don't get any points for it. You've got to at least show, the formula that you were using to come up with an answer, or your line of reasoning, or something about your calculations to get credit on these. So, so question 1, outline a recursive algorithm for computing n factorial. I just want you to write it, right? I mean, we've done this in class. N factorial is basically, n times n minus 1 factorial, but think about that and just sort of, write that out in words or formulas or something like that. That's not the question I'm going to grade for points on this, but think about that. And we're doing recursion in 222, so you're getting lots of examples of that. But think about, the recursive version of n factorial, which is really just, n factorial equals n times n minus 1 factorial. So if you were to write a function to calculate n factorial, what would that look like in terms of calling itself on n minus 1? So think about that. All right, and then the questions on counting. So question 2, you're making passwords and you want to know how many passwords are possible. So for A, we're constructing any password of 4 uppercase letters where you're allowed to repeat a character more than once, right? You can find this using the product rule. You can find this using, some version of combinations or permutations. Do what makes sense and justify your answer, right? I'm much more interested in seeing, something like, this times this, or p this comma that, than just a number, right? If you get the number right, and it happens to be exactly right, and I can see some of your work, that's good. If you show me the calculation and you don't actually put a number on there, that's good too. If you show me the number and there's no work, you probably don't get credit. And if you show me the number and the number is wrong, you definitely don't get credit. So show your calculations. 4 uppercase letters, repeats allowed. 4 uppercase letters, no repeats. So 4 distinct uppercase letters. How many passwords can you find? 4 uppercase letters have to start with the letter Z, no repeats. 6 uppercase letters must start with a Z followed by a Q, no repeats. 6 uppercase letters must begin with a Z or a Q, and no repeats are allowed. So these questions of how many passwords are possible, these are analogous to the question of in how many different ways can you form a password of 4 uppercase letters with repeats or without repeats, or starting with a Z, and so on. And so think product rule, maybe some rule, and come up with some formulas for these. We took a look at functions. Here's a binary function. It maps the numbers 1 through n into the values 0 or 1. How many possible functions are there? Question 4, you pick 8 integers from 1 to 10, including possibly 1 or 10, so inclusive, no repeats. What's the minimum number of pairs of integers that will add to exactly 11? Right? So you're going to pick 8 integers. And if you can pick 8 integers and none of them add to 11, your answer is 0, right? If you can pick 8 integers, but you're guaranteed that at least, one pair adds to 11, but you might be able to pick them so that there's not 2 pairs, then your answer would be 1. Right, so you're picking 8 integers from 1 to 10, and I want to know what's the guaranteed number of pairs that will add to 11 from what you've picked. Right, so this is a pigeonhole problem. And then question 5, the duck race, 6 ducks running a race, no ties possible. How many finishing orders are there for the 6 ducks? So this is messing around with permutations, combinations, things like that. All right, questions on that? Alright, so back to phrase structure grammars. So remember, we were looking at this question of describing a language, right, and trying to understand what symbols constitute a language over some vocabulary. So V is our vocabulary, equals finite set of symbols, and it can't be empty, so it's not the empty set. So the vocabulary is a finite set of symbols. Think, for example, the letters A through Z. Lambda was the empty string. So it's a string consisting of no symbols. V star equals a set of all words or strings, all words over V, which are strings comprised of symbols from V. So this is what we did on Monday. I'm just rehashing. Vocabulary is a finite set of symbols. A word over the vocabulary is a string comprised of symbols from that set V. And V star is a set of all such strings, all words over V. And then the thing we're after, which is a language over V, is just a subset of V star. So it's a particular set of strings where the strings are comprised of these symbols from the vocabulary. And we ended Monday by talking about how can we specify what constitutes a language, which subsets of, which elements of V star form our language. And one idea was to list rules for something to be included in the language, I before E except after C. Another one was to make an exhaustive list of all the strings that are words over V in our language, and so that's something like, Webster's dictionary. But the third approach is to use what's called a grammar. And a grammar is going to be basically a way to describe how we go from certain starting symbols to elements of our language, to strings that are contained in this language. So I want to begin this with a formal definition of what we call a phrase structure grammar. So a phrase structure grammar G, and it's going to be a 4-tuple. It's going to have 4 things to it. The first is V, that's our vocabulary. The second is T, that's what we're going to call terminal symbols. The third is a start symbol, and the fourth is a set of production rules. So V equals the vocabulary. Those are the things from which we create words. T equals a set of what we call terminal symbols. And that'll be a subset of the vocabulary. S will be a start symbol. And this is an element of the vocabulary. And P is where all the good stuff happens. This is a set of production rules. Production rules basically let us turn one string into another, or they let us produce or create strings from other strings. So let's just start with some examples, and then we'll get back to the formality later. But for example, here's a grammar, VTSP. All right, for this grammar, our vocabulary is going to be the following set of symbols: little a, little b, big A, big B, and Z. Our terminal symbols will be just little a and little b. Right, so it's a subset of the vocabulary. Our start symbol will be this symbol Z. And our production rules will be the following. So production rules look like this. They basically describe how one string can change into another string. So a Z can change into a big A, a big B, and a little a. That's one production rule. A big A can change into 2 big B's. That's another rule. A big B can change into a, little b, and a, big B can change into a B. So you're given these, and these 4 things describe a grammar. And here's how we use this tuple, right, VTSP, to describe the things that are part of our language. So, for example, we start with the start symbol, which is a Z. And we have a production rule which says Z can be changed into big A, big B, little a. And so I'm going to draw something like a tree, and I'm going to say, starting with Z, I can get big A, big B, little a. And what I'm trying to do is find a string comprised only of terminal symbols. So these other symbols that aren't terminal symbols, they're kind of like intermediates. They're like local variables. They're things that represent other things. But the words that are going to be part of my language are going to be comprised of these terminal symbols, in this case A and B, lowercase a, lowercase b. So I know that my start symbol Z can be an uppercase A, uppercase B, lowercase a. And I know that an uppercase A, uppercase B could be simply a B. And so from my start symbol, I can get to the string BA. And so this is part of my language. So I found one word in my language so far, little b, little a. All right, I could also start from my start symbol, and this becomes an A, B, A. And I know that an uppercase B can be changed into a little b, so this can be an A, This can be a little a, b, and this can be an a. And an a can be changed into two uppercase b's. And I'll just leave this as an a, b, and an a. And I know that each of these b's can be changed into an a, b, and an a, b. And so a, b, a, b, a, b, a, that's another string that's part of my language. So I found two words in my language. I could also take my start symbol z, change that into a, b, little a. I could use this rule to change the a into a pair of b's, and then a b followed by an a. And I can take each of these b's and change it into an a, b. And I'm going to get the same string a, b, a, b, a, b, a. And if you play around with this, you discover there are only two strings you can get from this language, BA and AB, AB, ABA. And so this phrase structure grammar describes a language with two words in it. Just these two words. Alright, so let's try another example. So I'll start this off the same. I'll have my same vocabulary, my same set of terminal symbols, my same start symbol, but let's have some different production rules. So my production rules are the following. I can go from my start symbol to a little a. I can go from my start symbol to an uppercase B followed by a little b. I can go from an uppercase A to a little a followed by a b. I can go from a big A to a little b followed by a big B, or I can go from a big B to the null string lambda. I'm making this up, so I don't know what this language will look like. But let's see what some of the strings are we can produce from this. So does anybody see one string that will be part of our language under this phrase structure grammar?
Can you turn Z into A?
Yes.
Well, I guess Z can also be capital B and B.
So we've got one string already. We know that a Z can be changed into an A, lowercase a, and that's a string comprised of terminal symbols. So A is one of the strings recognized by this language. Alright, and you said that Z could also be turned into an uppercase B followed by a little b. Can we turn that into something comprised of terminal symbols?
A capital B could be lowercase b and capital B.
So this could be a lowercase b followed by a capital B. And I'm not going to keep pulling the beat on. I'm just going to remember there's a B right here as well. And someone said something about lambda?
Yeah, capital B could also be lambda.
Yeah.
So I guess from there.
So let me do that here, and then we'll do it earlier also. So uppercase B can also be replaced by a lambda. And so a string containing B followed by an empty string followed by B, that's a string that's part of our language. And that's just BB. We don't actually put the lambda in there because lambda is just, it means a string of no length. So if we take a B and we put an empty string next to it and a B, we just get BB. But we could have also, taken a z to a big B, little b, and taken this b to a lambda. And so that would tell us that the string consisting of just b would also be part of our language. Cool, what else can we do?
I mean, you could just keep lowercase b repeating forever.
Yeah, we could go z comes down to a big B, little b, and a big B can be a little b followed by a big B, and this big B could be a little b followed by a big B, and this could be a little b followed by a big B, and this could be a lambda. And so B, 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 that's also part of our language. And in fact, any repetition of B's, one or more, will be part of our language. And so we sometimes represent that as like b to the n bigger than or equal to 1. This means, a single b or two b's or three b's. So it's a different notation that plays off the idea that if we were multiplying b by itself 4 times, it would look like this. So b to the n bigger than or equal to 1 means, a string consisting of one or more b's side by side. Any other strings in our language?
A, B3, N, where N is greater than or equal to 2.
Yeah, so Z...
No, 0, I guess. Something like that.
So Z, we know it can be an A. It can be a...
Oh, no, sorry, I was thinking of the A turning into AB.
Yeah, let me throw another one in here. Let's make it more interesting. So Z can turn into a big A, and big A could turn into an A followed by a big B. And B could be lambda, or it could be A followed by B, or it could be A followed by two B's. And so we can start, getting these strings in here. And so on. And so something like A times B to the N, and in this case, N bigger than or equal to 0, because, A times B to the 0, that's just A, and that's also part of our language. And so there's a more complex language, different production rules, you get different words over the language. And so the analysis part of this is what we're doing right now. We're looking at a phrase structure grammar, vocabulary, terminal, start symbol, and production rules, and we're analyzing it to figure out what are some of the words that are recognized by this language. And it's not a precise process. It's playing around with it. It's looking at the start symbol and seeing what it can turn into, and using these different production rules, trying to cover the space of possibilities, and then hopefully looking for patterns. Like, hey, any number of B's in a row seems to be a valid pattern. All right, so that's the spirit of how we're doing this. Let me make this more precise. So let's have some definitions. So suppose W0 is some string consisting of some stuff on the left, followed by some middle stuff, followed by some stuff on the right. Right? So all of these are just symbols for strings. So suppose W0 is a string consisting of, some string L, followed by some string Z0, followed by some string R. And suppose W1 is another string, which consists of the same stuff on the left, some different stuff in the middle, and then the same stuff on the end. Alright, so if there's a rule changing Z0 to Z1, in other words, if Z0 changes into Z1, is a member of the set of production rules, then we have the following definition. We say W1 is directly derivable from W0. So when we say W1 is directly derivable from W0, what we mean is that these strings are the same in the beginning and the end, but there's some part in the middle that's different. But we have a production rule which changes this thing into that thing. In other words, if we were to write this string out, we could take one production rule and say, oh, let's replace Z0 with Z1. Bingo, we've got this string W1 now. So that's the sense in which W1 is directly derivable from W0. And we have some symbology for this. W0 double arrow W1. All right, and then a similar definition. Suppose that W1 is directly derivable from W0, and suppose W2 is directly derivable from W1, and so on, up to some Wn is directly derivable from some Wn minus 1. Then we can say the following. We can say Wn is derivable from W0. So it's not directly derivable. There's no one production rule that goes from W0 to Wn. But there's a rule from W0 to W1, there's another rule from there to W2, and so on, and eventually there's a rule that gets us to Wn. So Wn is derivable from W0 means there's a sequence of production rules that will let us start with W0 and eventually get to Wn. And in this case, we have some symbology where we put a little asterisk on the top of this arrow. So Wn is derivable from W0. Here W1 is directly derivable from W0. And this is called a derivation. So the derivation is a sequence of direct derivations that tell you how to get from W0 to Wn in this case. And so in this case, for example, the string big B, little b, since we know that a big B can be replaced with a little b followed by a big B, this is directly derivable from that. Because that B, there's a production rule to change it into little b, big B. And so this is the empty string followed by this, followed by the empty string. This is, the empty string followed by this, followed by the empty string. Or if you like, this is the empty string, big B and a little b. This is the empty string, something we changed big B into, followed by little b. So this is directly derivable from that. We could also say that from the symbol Z, there is a derivation to little b, big B, little b. But we have to use a pair of production rules. All right, everybody got an idea what these definitions mean?
Isn't that relation between the Z derivation, little b, big B, little b, more like a chain rule?
It is a chain rule, yeah, exactly. It's a good way to put it. right? So this is really chaining these productions together. So saying something's derivable means that if we follow a chain of these direct derivations, we can get from the first thing to the last thing. And so we're going to use that chain rule notion in our most glorious definition of this section, which is the language generated by G. So the language generated by a grammar G, or sometimes we call it the language of G, this is equal to the set of all strings of terminal symbols which are derivable from S, the start symbol. So the language of G is just a set of strings that are derivable from S, where those strings are comprised strictly of whatever your terminal symbols are. And in the language of set theory, this is equal to the set of all words in T star, the set of all finite length strings of terminal symbols, such that there is a derivation from S to that word. So that's what the language of a grammar is. It's a very short definition in set theory, but it's, you know, a bunch of pages of build-up. But the effect of this is, you know, we're going to basically start with start symbol. We're going to apply production rules until we get to a string consisting of just terminal symbols. That's a word in our language. And the whole language is just a set of all words that we can get to from that starting point. All right, so let's do some more examples of this. So our vocabulary is going to be a Z, A, and a, little b. Our terminal symbols will be little a, little b. Our start symbol will be Z, not our symbol. And our production rules will be the following. So we can go from the start symbol to little a, big A. We can go from the start symbol to a little b. And we can go from a big A to a small a, small a. So what is the language of this grammar? So we want to find all the strings of terminal symbols we can get to from Z. And there's one that jumps out right away from the production rules. So what's one string we can get to?
3 little a's.
Okay, that's not as direct as the one I was thinking. Yeah, so B is definitely one. We can go from Z directly to B. Or we can go from Z to a little a followed by a big A, and that big A goes to 2 A's, so we can basically go from Z to 3 A's. And that's really it. So good, you found the whole language. And in this case, you know, the language is finite. It contains only 2 strings. But the language could be infinite. So let's look at a different example. Our vocabulary is going to be a start symbol, a 0, and a 1. Our terminal symbols will be a 0 and a 1. Our start symbol will be Z, and our production rules will be the following. So Z can go to a 1, 1 followed by a Z, or Z can go to a 0. So let's find some words in our language. So any ideas?
Shouldn't Z be 1-1Z?
Z could be a 1-1Z. Definitely. And we're not ready to put this into our language because it's got non-terminals.
Then you could just like keep going on forever, right? With the Z, or you can just make that Z into a 0.
Right, so we could do, you know, 1 1 1 1 1 1 0. Or we could have, you know, at this point taken the Z down to be a 0 and gotten a 1 1 1 1 0. Or in fact, we have a production rule which says Z can simply be a 0, so we could have just put in a 0. Or that, and so on. So how many things are contained in the language? How many words are recognized by this language?
Infinite.
An infinite number of them, which is pretty cool. Because, you know, describing the language didn't take an infinite amount of paper. It was this much paper. But we've described a language with an infinite number of words in it. And each of these words has a finite length. But there's no limit to how long a word could be in this language. We can find a word in this language that's 1,000,001 characters. It's 1,000,000 ones followed by a 0. We could find a word with 1,000,001 characters. But each word is still finite in length. But there's no limit to how large a word could be found in this language. And we could write this maybe like this in shorthand. A pair of 1s repeated n times followed by a 0, where that repetition is either 0 or more repetitions of 1 1. So if n is 0, it's this. If n is 1, it's this. If n is 2, it's this, and so on. All right, good. I think people are getting this. Let's try another example. So our vocabulary here will be a start symbol, a 0, a 1, but also an A or a B. Our terminal symbols will still just be 0, 1. Our start symbol will be Z. And our production rules will be the following. So we can go from a start symbol to 0A. We can go from a start symbol to 1A. We can go from an A to 0B. We can go from B to 1A. And we can go from a B to a 1. So can we find any strings of terminal symbols in here?
The first Z can turn into 0A, capital A.
Okay. So let me draw my derivation tree a little differently. Z could go to a 0A. What can an A go to?
0 capital B.
A goes to 0 capital B. And what can a B go to?
Well, we have two options, either 1A or 1.
So this could go to 1A or it could go to 1. If it goes to a 1, we've got a string of terminal symbols, 0, 0, 1. So that's one word. If it goes to a 1A, what does an A go to? Well, it goes to a 0B. And a B can go to either a 1A or a 1. If it goes to a 1, we've got a 0, 0, 1, 0, 1. If it goes to a 1A, this A goes to a 0B, and that goes to either a 1A or a 1. If it goes to a 1, we have a 0, 0, 1, 0, 1, 0, 1. If it goes over here, we can keep doing this and eventually, you know, come down to going off to the right to a 1. And so just thinking about these and, you know, sort of repeating the pattern. Can we write that in some kind of nicer shorthand, you know, something like this?
Yeah, so it'd be 0, 0, 1, and then paren 0, 1, and greater than or equal to 0.
Cool. A 0, 0, 1 followed by 0 or more repetitions of 0, 1. N is 0, N is 1, N is 2, N is 3, and so on. Awesome. We could rewrite this a little differently also. We could actually take this 0, 1 and put it in here. And just require N to be bigger than or equal to 1. And that would also cover the same sets. Both are equally correct.
Yeah, I didn't think about pulling that 0. Yeah.
Yeah, that's cool. This is a Z, not an S. All right, so we have another possibility. This was the possibility where Z went to 0A, but Z could also go to 1A, and an A changes into a 0B, and that B either changes to a 1 or into a 1A, and that A changes to a 0B, which becomes either a 1A or a 1, and so on. So we have another set of strings possible. We have a 1, 0, 1. We have a 1, 0, 1, 0, 1. If we believe this pattern, we have a 1, 0, 1, 0, 1, 0, 1, and so on.
So it's 0, 1 to the N, followed by a 1.
Actually,
1, 0.
yeah, so this is 1, 0 to the
1, 0.
N, followed by a 1,
By 1.
N bigger than or equal to 1.
1. Yeah.
Cool. So, and I think those are all the possibilities. So the language of G would be either a 0 followed by 0, 1 to the N, N bigger or equal to 1, or, let me use a different variable, 1, 0 to the M followed by a 1, M bigger than or equal to 1. So that's a different language, right? Doesn't mean anything in particular. It's kind of a random example, but you know, this is how we analyze, given the 4 elements of a grammar, what kinds of strings are recognized by the language. So that's the analysis process. The flip side of that is synthesis. Suppose we have a language and we want to write a grammar to recognize it. And this is a very different type of feeling. So for example, suppose we have a language which contains the following elements. The empty string, a 0, 1, a pair of zeros followed by a pair of ones, 3 zeros followed by 3 ones, and so on. Which we could write succinctly as, you know, 0 to the n, 1 to the n, where n is bigger than or equal to 0. So this would be n is 0, this is n is 1, this is n is 2, and so on. It's some number of zeros followed by the same number of ones. And if we want to describe a grammar for this, well, our grammar is certainly going to have to contain zeros and ones and some kind of start symbol. It may include some other stuff, right? Some of these other languages we've been playing with, we included, you know, things that were effectively like temporary variables. And so we may have other stuff in there. But our goal is to construct strings of terminal symbols 0 and 1. I'm going to use the start symbol of Z, and then the real magic is, what are the production rules? So can you think of at least one production rule that will give us an element of our language? Hey, how's it going? So think of a really simple production rule.
We're trying to get 0 to the n, 1 to the n.
Yeah, something that'll return this. But here's a set of you know, representatives of the kinds of words we want to represent. And forget about maybe the bigger problem. Let's just find a rule that returns, you know, 1 or 2 of these. Because we're just kind of starting the synthesis process.
Okay, so, I mean, if Z returns lambda.
Yeah, that's a perfectly good rule. Z could just go into the empty string. And now if I analyze this and I say, well, what strings are derivable from Z? Well, there's one right there. It's directly derivable. That gets us that word. So that's a good rule.
Probably Z derives 0, Z.
So 0Z is the right idea, but if we let Z go into 0Z, and we let Z go into lambda, that would give us just the string 0, and that's not part of the language. But this is really close. Can we tweak this rule a little bit?
Simple. I guess it needs to go to 0, 1, but I don't really enjoy that.
Yeah, we could do Z to 0, 1. That would pick this up.
Yeah.
And then we started looking for, you know, something more general. And this is, it's like physics problems again, right? I say that a lot. There's no algorithm we have to follow to say, okay, here's how you come up with a set of production rules. It's a question of looking at the strings you want to include and trying to find patterns. And let me point out a pattern of these strings. If I take any of these strings other than the empty string, and I lop off that first 0 and that last 1, what am I left with? Something else that belongs to the language. 3 zeros and 3 ones. And if I were to lop off that first 0 and that last 1, I get something else that belongs to the language. And so if my production rules are going to take my start symbol Z into something in this language,
0, Z1.
take Z into 0, Z1, that's going to be all I need.
Okay.
Because now Z could go into just the empty string, or it could go into a 0 followed by Z followed by 1. Well, what is this Z going to be? It could be the empty string, in which case we've got the string 0, 1, or it could be a 0 followed by z followed by 1. So we've got 2 zeros, a z, and 2 1s, and if this comes down to lambda, there's that string right there. If it comes down to 0, z, 1, and this comes down to lambda, there's 0, 0, 0, empty string 1, 1, 1, there's that string. So there's a set of production rules as part of this grammar that produces this language exactly. All right, so does everybody see the analysis part of this, that this grammar will define this language? Ask questions if that part's not clear. So let's try another synthesis example. Suppose we want a language consisting of one or more consecutive zeros, and those are the only strings. So it consists of, 0, double 0, triple 0, and so on. And, throughout all of this, we'll stick with a start symbol of z, a set of terminal symbols of 0, 1, a vocabulary of at least 0, 1 in the start symbol, and maybe some other stuff. And mostly we're asking, what are the production rules? So what could we change our start symbol into to get a repetition of zeros?
Z equals 0z.
Nice. Take a z into a 0z. So now z could be a 0z, and this z could be a 0z, and this z could be a 0z. So we're getting a arbitrarily long string of zeros. And we want one more rule in here to make sure that this chain of derivations eventually stops. So what's another thing that z could go to?
It could just go into 0.
Could just go into 0. You got it. There's a perfect set of production rules. So z can become a 0. That's that string. Or it could become a 0z. And this z could just become a 0, so now we've got 2 zeros. Or it could become a 0z, and this z could become a 0, so now we've got 0, 0, 0. There's our 3 zeros, and so on. And this will define this exact language perfectly. All right, let's keep going. Suppose we want an even number of zeros. So double 0 to the n, where n is bigger than or equal to 1. And we can get there with a little bit of a tweak on our previous example.
Instead of just 1 0, make it 2.
Yeah, let's take z to double 0 z, or z to double 0. So start symbol can go to 2 zeros, that's that. It could go to 2 zeros followed by a Z, which might be this, there's 4 zeros. Or 2 zeros followed by a Z, which could be another 2 zeros followed by a Z, which is 2 zeros. There's our 6 zeros. So we start to develop a bit of an intuition for, based on the pattern of strings that we're trying to describe, how can we cobble together some rules to generate that language. And it becomes a bit of a programming exercise. And so let me do one more example before a break. Let's try to generate strings of the form 0 to the m, 1 to the n, where n and m are bigger than or equal to 1. So we want strings like, 0, 1, 0, 0, 1, 0, 0, 1, 1, bunch of zeros followed by a bunch of ones, and so on. And this is basically, at least 1 0, but any number of zeros followed by 1 or more ones. Any thoughts how to tackle coming up with a set of production rules for this?
I'm thinking make C equal to like A, B, and then A equal to 0 and 1 and B equal to 0 and 1 or something like that.
Cool. No, that's exactly right. So we can modularize this, right? We can break this into functions. Let's take our start symbol into two strings A and B. And let's define production rules so that A is a collection of zeros and B is a collection of ones. So what do those rules look like? Well, we just did one of them when we found, collections of zeros. So we could take A to be a 0, or we could take A to be a 0 followed by an A, and we can take B to be a 1 or B to be a 1 followed by a B. And if we analyze this, right, A will be a 0 followed by, 0 or more other zeros. So A basically changes into a string of zeros. And B becomes a 1 or a 1 followed by a 1 or a 1 followed by a 1 followed by 1. B is a string of ones. And our start symbol changes into 1 or more zeros followed by 1 or more ones. And so there's a set of production rules for that language. So even though this may seem like, kind of quirky and clunky, when you start working with it more and more, you start to develop these intuitions. And you can start to see not just that you have to be lucky and, think of the magic production rule. You start to see how to actually craft these production rules, how to actually describe what you're after by putting together, things that describe smaller versions of the problem. And so this is very much like a programming feel, where we break problems down into smaller problems and then put those together. All right, so let's stretch our brains for about 5 minutes, and then we'll come back and take a look at a different way of representing syntax. So we'll come back at about 2:07. All right. So let's continue thinking about ways to describe languages, and this is a fairly theoretical way to do this. It's very formal. It lets us, rigorously describe what is or isn't part of a language, and it lets us derive things that are part of a language. But it's not the most directly useful way to think about what constitutes a language. And so a possibly more useful approach is something called Backus-Naur form. It's usually just called BNF. And BNF is a way to describe what constitutes a language, and we can think of, for example, a programming language.
What was that?
Backus-Naur form. It's two names, Backus-Naur. But everyone just calls it BNF. And the way this generally works is we write a series of rules which describe one thing in terms of other things. And so we put inside angle brackets some kind of identifier, colon equals equals, and then we list, some expression inside angle brackets, maybe followed by, some other expression. We can use a pipe to say or, something else, or, and so on and so forth. And these could be, strings of terminal symbols, or they could be other identifiers that are described in other lines, and so on and so forth. And so it's the same idea of, transforming one thing into another, deriving one thing from another, but it writes out a little more intuitively. So let me give you an example of a signed integer. So, you're writing a programming language and you're at a point in your program where you're looking for a number. And it should be an integer, and it could be positive, negative, or 0. And so you want to describe what it means to be a signed integer. Now, we can think of this intuitively, right? It's a bunch of digits, possibly followed by a minus sign in the beginning, possibly followed by a plus sign in the beginning, preceded by a plus sign or minus sign in the beginning. And maybe we don't allow leading zeros, maybe we do. We're not going to worry about it. So it's basically, either just a string of digits or a string of digits preceded by a minus sign or a plus sign. And so here's a way we could describe this in BNF. So we could say, this identifier called a signed int is equal to a sign followed by an int. And a sign is equal to a plus or a minus or lambda, an empty string. And an int is defined to be either a digit followed by an int or just a digit. And a digit is defined to be a 0 or a 1 or a 2 or a 3 or a 4 and so on. And so there's a whole definition for a signed integer. And, if we have a string like 23, well, that's a pair of digits. Well, a pair of digits is a digit followed by an int, because 3 is also an int, because an int can be a digit. So since an int can be a digit, 3 is an int. And since a 2 can be a digit, a 2 followed by a 3 has the form of a digit followed by an integer, so 2, 3 is also an int. And 1, 2, 3 is also a digit 1 followed by an int 2, 3. So int captures basically any collection of one or more digits. And then a sign is either a plus sign, a minus sign, or nothing. And so a signed int is a collection of one or more digits preceded by either nothing or a plus or a minus sign. And so there's the BNF for a signed integer. And this starts to be pretty easy and pretty straightforward way to think about syntax of things like programming languages. If you wanted to write a compiler, you might start by describing a BNF for the language. And that completely describes what is or is not a legal program in that language. And so you can download, for example, the syntax of C in BNF. And C has lots of sort of like, you know, kind of edgy things that we don't usually deal with beyond, you know, just sort of like main blah blah curly bracket. But, you know, if you kind of dig down into this, you know, what's a constant expression? It's a conditional expression. What's a conditional expression? It's a logical OR expression, or it's a logical OR expression followed by a question mark, followed by an expression, followed by a conditional expression. And you can go through this and you can do a few things. One, you could create syntactically legal programs by using these, or you can take a program and see if it matches this pattern. So an additive expression is a multiplicative expression, or an additive expression plus a multiplicative, or an additive minus a multiplicative. And a multiplicative can be a cast, or, you know, a multiplicative times a cast divided by or modulo a cast, and so on. And this is the whole language, and it's 4 pages.
Not gonna lie, I thought it would be like way more than that.
Yeah, it's surprisingly short, but C is a very syntactically simple language. It doesn't include print statements, for example. Prints and inputs and things like that are function calls. So as a language, it's simpler than, say, Pascal. But this covers, like, you know, every statement that you can write, every program that you can make in C is described by this 4-page BNF. And it doesn't necessarily hold a lot of meaning when you look at it, except maybe, you know, the different ways you can assign a value to a variable. Well, there's the plain old equals sign, or star equals, or plus equals for, you know, adding something to itself, and so on. The unary operators are things that work with just a single operand, so address of, or dereferencing a pointer, and so on and so forth. But if you work your way back up through these, right, you'll see that this captures arithmetic expressions and complex assignment statements and complex if statements, and so on and so forth. And with something like this, you've got a good start on writing something like a compiler. And this is so sort of programmatic to do that there are tools out there that will take something like a BNF and create a compiler for you. And so there's a tool called Yak, which is yet another compiler. It's a parser generator. It takes a description of a language and generates a set of code that will tell you if an input matches that description of the language. And so Yak and Bison are tools that you can use when you're writing compilers, and they do a lot of kind of the boilerplate mechanics of parsing and such, along with Lex. And so BNF is a fun language to play around with, a fun tool to play around with. and just kind of for kicks, here's a BNF for an arithmetic expression. So an expression is either a left expression, an operator, and an expression, or it's just a left expression, or it's a minus sign followed by an expression. And the left expression is a variable, or a number, or a pair of parentheses with an expression inside. My only operations are plus, minus, times, divide. My variables are alphas, alphabetic characters followed by variables or alphas. And a number is a digit followed by a number or a digit. And so this captures the idea of a variable as something that starts with a letter, and is followed by other stuff. And this is a digit, which is a succession of digits gives you a number, and so on. And this is a package that lets you take a BNF and basically write C code to process an input string according to a BNF. And so, for example, to parse an expression, I can look for a minus sign followed by an expression. So this says let's make a state transition if we find a minus sign. Let's absorb that and let's go to state S4. And state S4 says try to find an expression. And if you find that, you've succeeded. But an expression could also be a left expression. And if I find a left expression, I'll go to state S5 and look for an operator. And if I find an operator, I'll go to state S6, and S6 will look for another expression. So that's a left expression, an operator, and an expression. And if I find that, I'll return success. If I was looking for an expression and all I found was a left expression, right, I went down to S5 and I did not find an operator, I'll say, okay, if you find lambda, an empty string, consider that success. Well, that picks up the fact that an expression is just a left expression. And so starting with a BNF, you can write these state transition instructions directly from the BNF itself. Right? A variable is an alpha followed by a variable or an alpha. So I have a state called variable, which says I need an alpha followed by an svar1, which is a variable, or just an alpha, right? And so this is recursive. A variable is an alpha followed by a variable, or it's an alpha followed by nothing. And so this is a package I put together decades ago, based on a assembly language library on an old system called VMS that had a facility for parsing things based on BNF. And so I ported it to C, and I basically have all of these C macros that you can use. They come in this parse.h file. And once you describe this BNF, you can parse input by just calling parse, right? And it will return a 1 or a 0. And if it returns a 0, something went wrong. If it returns a 1, it was successful. If it returns a 0, there's an error, and there's this variable max string, which should point to where the parse failed. And so this is, you know, a relatively short main program. And if we run this, and I don't guarantee I remember how to use this, but you know, 2 times 3 is fine. This is fine. This has got a problem, right? It's looking for an extra closing parentheses there. Right, this has got a problem right there at that asterisk. It shouldn't be followed by a divide symbol. And so starting with the idea of a BNF, you can turn this into code pretty easily. And things like Yak and Lex and so on will do some of this for you. But this is a pretty close to the metal rendering of these expressions into something that basically parses. And when you do this kind of parsing, what you're actually doing is you're building a state machine. And right, you don't have to know this for the exam or anything. It's just an example. But the idea is, right, I'm going to start off where I'm trying to parse an expression. And so if I find a left expression, I'm going to go into a different state where I'm looking for an operator. And if I find an operator, then I'll go to a state where I'm looking for an expression. Or if I'm looking for a left expression and I don't find an operator, I'll say, okay, well, that's good. I've got my string. So I could describe this process of parsing a language as some kind of state machine, where I'm starting here in a state and I'm trying to parse an expression. So if I have a left expression, I'll come to this other state, and if I have an operator, then I need to, right, I have a left expression followed by an operator. What I need next is an expression. And so here I'm looking for an expression. Well, this is the block where I'm looking for an expression, so I can really go back in here. And if I find an expression and I don't have an operator, right, I could sort of say, you know, this is a success state because I found a left expression. Or if I'm looking for an expression and I find a minus sign, I could go into a state that says, okay, now let's look for an expression. So yes, state machines are back. So let's make this a little more formal. But again, we're not going to talk about flip-flops. We're not going to make those big wide tables of pain where we have, you know, inputs and all that kind of stuff. I'll try not to use any J's or K's. But these are the same state machines from Engineering 250. Except in 250, you know, we're actually designing them at the chip and gate level. And here we're thinking of them more abstractly. So, general notion of a finite state machine, we can think of it as a set of four tuples, which basically say, you know, present state, input, output, and next state. And the whole nature of a state machine is what this collection of four tuples is. If you're in this state and you have this input, generate this output and go to that state. And that's all that state machines do all day long. They look at some input, they see what their present state is. If they find a rule which says for that input in that present state, they produce an output and they go to a new state. So let's see an example of a state machine. And you may recognize this from Engineering 250 if you took 250 with me. So here's the present state, and here's an input, and the input's going to be a 1 or a 0 based on what the weather is today, whether the weather is sunny or rainy. And the state is going to predict what tomorrow's weather is. So this state up here says definitely sunny. And if we're predicting that if we predicted that today was definitely going to be sunny, and in fact the sun is out today, our prediction for tomorrow will still be definitely sunny. if we're in this state because we predicted that today's weather would be sunny, but in fact it's raining, we're going to change our prediction for tomorrow to be probably sunny. And if we predict tomorrow to be probably sunny and it turns out to be sunny, we'll go back and the next day we'll say definitely sunny because it's been sunny 2 days in a row. But you know, we said it was going to be sunny and it rained, so we said, okay, tomorrow's probably sunny. If it rains again, then we're going to say probably rain the next day. And if in fact it does rain the next day, then we'll say definitely going to rain tomorrow. But if we predict it's going to rain and it turns out to be sunny, well, that's just one sunny day, but we live in the Northwest, so we're still going to say, you know, it's probably going to rain tomorrow. But if it turns out to be sunny a second day in a row, we'll say, yeah, it'll probably be sunny tomorrow. We're not ready to say definite, because 2 sunny days in a row, who knows? But, you know, if it's sunny and it's sunny, then it's sunny on that third day. Now we're ready to say, oh, we're in a patch of sunshine now. It's definitely going to be sunny tomorrow. So here's a weather predicting machine. And basically we have, you know, a prediction for what today was going to be, and based on whether or not today is sunny or rainy, we come up with a new prediction for tomorrow. And so this is a state machine. We have 4 states, and we could, you know, make a table for this. If your current state is definitely sunny and your input is a 1, then your next state should be definitely sunny. And our output would be, you know, it's going to be sunny tomorrow. If your present state is definitely sunny and it's raining, then our new state will be probably sunny, and our output is, yeah, it's going to be sunny tomorrow. And so on. And so this is a weather predictor. It's also a mood predictor, which I do in 250, I think, where it's like, you know, what's your mood going to be tomorrow? Well, it's based on whether or not it's raining 2 days in a row and so on. This is also what's called a branch predictor. And inside most modern CPUs, there's a little state machine that does exactly this. Oh, I forgot my other condition here. There's a 0. This is called a 2-bit branch predictor. And it's used when you're coming up to a branch statement. You're looking ahead at your instructions because you're prefetching, you're filling a pipeline. If you've done 270, you know this. If not, don't worry about it. But you're trying to predict ahead of time, when I get to this conditional branch, so if such and such do something, else do something else. If you can predict which instructions you're going to execute, you can run your CPU a lot faster. So in a CPU, you have a set of instructions. When you're executing this instruction, part of your hardware is looking at this instruction 4 or 5 steps later and getting ready to execute it. Right? This is essential to get, you know, the multi-gigahertz clock speeds that we can sustain. But this look ahead is problematic when you have conditional statements. If x equals 0, I want to do this thing, otherwise I want to do that thing. Well, if I'm 5 instructions back, I don't know what the value of x is yet. So I can't predict when I get here, am I going to do this or am I going to do that? And that's a problem. So there's a little genie inside your CPU that makes a really good guess whether or not this condition is going to be true or false before it gets there. And it does it using a state machine like this. And the basic logic is, each time it gets to one of these conditions, it remembers whether the condition was true or false. And the next time it's coming up and it sees, you know, 5 instructions later, here's an if statement, it will check back and say, hey, last time I did this, was this true or false? If it was false, I'll say, okay, it's probably going to be false. I'll go ahead and get ready to execute the else statement. But just doing what you did last time, not a terribly good prediction. But something like this, which says, you know, if the last 2 times this condition was false, I'm pretty sure that the next time I see this, it's going to be false also. And if it's been false, 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 and one time it was true, I'm still going to say, hey, it's probably going to be false next time. But if it turns out to be true 2 times in a row, and now I switch my tune and I say, okay, it's probably going to be true next time. And this works because of nested loops. It works because when you have a for loop where you're iterating, chances are when you get to the bottom of the loop, you're going to keep going back up to the top. But once in a while, you're not going to. You're going to fall through because your loop hit its terminal condition. But if that's inside another loop, the next time you come to that test, you're going to branch again. And that's what this is capturing. And nested loops pop up a lot in time intensive. So there's an example of a state machine that's actually part of most computer architectures. All right, so that's enough engineering 250. Let's look at this in terms of languages. So state machines and languages. And so how can we use state machines with strings? So here's a machine with 2 states. And let me just call this S1 and S0. Let me put a star here to say this is the initial state. And my machine's going to look like this. If I have a 1, I'm going to output a 1 and go to S0. If I have a 0, I'm going to output a 0 and go to S0. From S0, if I have a 0, I'll output a 1 and go to S1. And from S0, if I have a 1, I'll output a 0 and go to S1. So here's our key. And on each arrow, I'm drawing an input/output. So suppose my input is 4 zeros and 4 ones. All right, so we grab the first input. It's a 0. And we're starting off in state S1. If my input is a 0, I'm going to output a 0, and I'm going to go to state S0. So now I'm in state S0. Here's my second bit, which is a 0. And this rule says if my input is a 0, let's output a 1 and go to S1. Here's my third input is a 0, same thing, I'm going to output a 0, go to S0. Here's my fourth input is a 0, same thing, I'm going to output a 1 and go to S1. My fifth input is a 1, my rule says if I've got a 1, let's output a 1 and go to S0. My sixth bit is a 1, and if I'm in S0 and my input's a 1, I'm going to output a 0 and go to S0. And then again, if I've got a 1, I'll output a 1, go to S0. If I've got a 1, I'll output a 0 and go to S1. So my input looked like this. And my output looked like this. So what does this machine do to an input string in general? Can you characterize this in some sort of description?
It's shifting bits.
It's a bit like a shift, no pun intended.
It's like moving. Let's see here.
It's not exactly a shift, though.
It's like spacing them out.
Okay.
Like inserting them into other places. I don't know.
So what about the states? How do we move between states? We start off in state 1. Do we know what the next state's going to be?
Yes.
It's guaranteed to be 0 regardless of what our input is. And if we're in state 0 regardless of what our input is, we're going to go to state 1. So this machine keeps alternating. State 1, state 0, state 1, state 0.
And then it's flipping the bit on the second.
Yes, if we're in state 0, it flips the input bit to get the output. If we're in state 1, it preserves the input bit to get the output. And since it's alternating between these, here's what it does. It starts off, it preserves the input, and then it toggles the input, and then it preserves the input, and then it toggles it. And so this takes an input string, and it toggles every other bit.
Yeah.
So that's a finite state machine. It has 2 states, but this can operate on an infinitely long input string if we want, and it will produce the correct infinitely long output string. So we can do manipulation of strings like this. Well, if we can manipulate strings, we should be able to analyze strings. And so it turns out we can do that. We can use state machines for language recognition. And so when we draw a state diagram, and we're not going to make state machines, we're just going to stick with diagrams. When we draw a state diagram for a language recognition system, we're going to have a starting state. We're going to have, circles with arrows and inputs and outputs and stuff like that. But we're going to have what we call recognized states. And a recognized state is a state that if we get there, it means we've recognized what the input string is. We've seen this as part of our language. And so here's an example. Here's a state S0. And if we have a 1, we'll go to S1. And if we have, and I'm going to be, kind of lazy here. Instead of drawing 2 arrows, one for a 0, one for a 1, I'm just going to say whether we have a 0 or a 1, we're going to go to state S2. And over here, if we have a 0, we'll go to state S2. And in state S2, if we have a 0 or a 1, we'll stay in state S2. But I'm going to draw this state with a double circle. And so a state with 2 circles is what we call a recognized state. And I'm going to put a little asterisk here, and the asterisk means this is the initial state. So here's the plan. We start in the initial state. We have an input string. We grab characters or symbols from that string and we move around from state to state. Anytime we get to a recognized state, the piece of the word we've seen up to that is recognized by the language. So this is a different way we're going to make something that can understand, when it's seen something that's valid as part of a language. So starting with state S0, what sorts of bit patterns, what are some bit patterns that will take us to state S2? So what are some of the recognized strings of bits?
1, either a 0 or 1.
Yeah, a 1 followed by a 0, right? A 1 will take us here, a 0 will take us there. That's a recognized state. Or a 1 followed by a 1, start off with a 1, take a 1 in there. That's a recognized state. What else?
Just a 0?
Just plain old 0. Because if we start in S0, a 0 takes us to a recognized state. What else? Once we're in state 2, if we get a 0 or a 1, that's going to take us back to state 2. So for example, 1, 0, 1 would also be recognized. And in fact, 1, 0 followed by any pattern of 0s or 1s would still take us back to S2. It would still be a recognized state. And so this is actually a fairly uninteresting machine because it recognizes pretty much every string of ones and zeros, except for a string consisting of just a single one. But a 0 followed by any pattern of zeros and ones, or a 1 followed by any pattern of zeros or ones would be recognized. So let's try something a little more interesting. So here's S0. This is our start state. And if we have a 1, we're going to come back to S0. Here's our recognized state, S1. And if we have a 0, we'll go to S1. From S1, if we have a 1, we'll go to S1. And if we have a 0, we'll go back to S0. So think about this for a minute, and let's find some strings that are recognized by this. So any strings?
I'm not gonna lie, spaced out for a sec. What was the question?
What are some strings recognized by this machine?
Okay. Well, 0.
Cool.
Just one?
Actually a 1 will leave us in S0. So that's not recognized.
0, 1.
0, 1. That will leave us in a recognized state.
0, 0.
0, 0 will bring us back to S0. So that won't be recognized, but there's something
Okay.
close to that.
0, 1 continuous?
Yep, 0 followed by any number of ones will be recognized. What else?
0, 0 followed by any number of 1 zeros.
Let's see, 0, 0 followed by a 1, 0.
Oh, sorry. Yeah, sorry. So 0, 0 followed by 1, 0. And so just repeating any of that group, I guess.
Alright, can you say that again?
So it's 0 followed by any number of 0, 1, 0, 1, 0.
0 followed by any number of 0, 1, 0,
Something
1.
like that.
Something like that.
Yeah, it's along those lines.
Okay. Can anyone see what this machine is kind of doing? Or what's happening in each state? Or what is it that has to happen for us to get to a particular stage?
Oh, anytime it's 0, it switches states.
Anytime there's a 0, it switches states. So if we get a 0, we go to S1. If we get another one, we go to S0. If we get a third one, we go to S1. Fourth one to S0. Fifth one goes to S1. So 0, we change state. What do ones do?
They just remain in that state.
Yeah, 1 has no effect on our state. The zeros are the only things that cause us to change state. And so if we have 1, 0, that's recognized, because that'll put us in S1. A second 0 will leave us unrecognized, but a third 0 would also be recognized. And a fourth one would bring us back to S0, but a fifth 0 would put us in our recognized state again. So is there a pattern here?
Yeah, every odd 0.
Yeah, if you have an odd number of zeros, you're going to be in a recognized state. And the ones don't change whether you're recognized or not. So this machine recognizes any string with an odd number of zeros. That's pretty cool. We could use that for like parity generation if we wanted to generate even or odd parity to do serial data transmission. Well, there's a state machine for counting whether we have an even or odd number of zeros. How about if we wanted to recognize a string containing a 1 followed by an even number of zeros? So we'll start off here. We need to have a 1. So if we have a 1, we'll transition into some other state. If we start off with a 0, well, when we say we want to recognize a 1 with an even number of zeros, there's two questions. Are we only recognizing strings that begin with a 1 followed by an even number of zeros? Or if we get a string like, 0, 0, 1, 1, 1, 0, 0, would we get to this point and say, oh, there's a 1 followed by an even number of zeros? So I'm going to suppose we're thinking like this. It's the more forgiving key entry system, right? Where if you happen to type in the right 4 digits anytime, you get the door unlocked. So if we have a 0, I'm just going to stay in state 0. And state 0 basically says I'm waiting for the person to enter a 1. Once we get a 1, we'll come over here to state 1. And, if you just type a 1, that is a 1 followed by an even number of zeros. And so we'll call that, a recognized state. And once you're here, if you find a 0, we'll go to some other state. But if you find another 0, guess what? You had a 1 followed by an even number of zeros. You just found a 0, 0. You're back to a recognized state. And if you're in here and you find a 1, so you typed in something like a 1, 0, 0, and a 1, well, we could go back to the starting state, or we could say, this is a 1 followed by 0 zeros. So we could actually have this go back here. And so again, the more you play with these, the more you analyze these state machines, the more you start to be able to see how to construct a machine to do a certain task, recognize a certain string. And you can start piecing these things together. If you want to recognize one thing followed by another thing, you could make a machine for that first thing. And once you find that, transition to another machine that recognizes the second thing, and so on and so forth. So state machines, they pop up in digital logic. They pop up in programming. 223, we're going to be, making games and things like that, where we're going to need to keep track of the current state of the system. And it's going to need to know, whose turn is it, and you know, how many of such and such are on the playing field and so on. It's going to be a state machine implemented in software. In your stack queue problem from CSE215, the person was going to type an enter key. You needed to either pop from a stack or remove from a queue. But there's nothing different in what the person typed. They just hit the enter key. Your program needed to know, what are they going to do? Should we remove from the queue or should we pop from the stack? The way you knew that was because you had a state variable. And you can think of your whole program as a state machine, and if it's in stack mode and the person hits a return, pop the stack. If you're in queue mode and the person hits return, remove from the queue. So state machines implemented as software programs, a very common thing to do. And as we move into, you know, more advanced programming, we get into event-driven programming, making things like, you know, interactive games and so on. We'll be using this idea of state and moving from one state to another more and more. And so this is, you know, topical to where we're going with programming, but it's also tied into the origin of all of this. And so you know, one of the earliest state machines is something called a Turing machine. And these go back, you know, almost 100 years. And Turing machines were developed as theoretical models of computation. And so we're going to describe what a Turing machine is, and look at what programs on a Turing machine look like, and do some analysis of Turing machines, and you'll have some homework questions on this and so on. But Turing machines were developed as a theoretical concept. A fictitious model of something that could follow algorithms and do computation. And I don't think anybody envisioned at the time that Turing machines would one day be, you know, one of the most popular machines on the planet. And all of the computers that we use, our smartphones, our processor inside the microwave oven, these things are basically Turing machines. So this is a theoretical model of computation, but you know, it's very much applicable to the actual hardware that we use as programmers. So a Turing machine T, and you know, as usual, we'll make this sound fancier than it needs to. And we'll do some definitions, and we'll talk about four tuples and things like that. So a Turing machine is a four tuple. S, I, curly F, and S0. Okay, S is a set of states. I is an alphabet. I guess I could have called that A for alphabet. And the alphabet is going to include a blank, which I'll just write as a B with a slash through it. S0 is an initial state. And F is a set of rules. Right? Not totally unlike grammar that we were describing earlier, right? So a set of states, an initial state, an alphabet, and then a set of rules. And if we want to be more fancy about this, F is a function. Goes from the Cartesian product of S and I into a Cartesian product of S, I, and a set consisting of two symbols R and L. I'm putting that there just because I can't help it, but don't worry about it. Let's do some specific examples. Okay, so the idea is we're going to have a set of states. We're going to have some initial state you start in. We have some alphabet of symbols, and then a set of rules. And the rules will do the following. They will say if you are in this state, and if the current input symbol is some particular symbol, right? So it tells you what to do with each combination of state and input symbol. Go to a new state with some new symbol written onto the input tape, and then we're going to do either an R or an L, and this is going to translate to moving a piece of input tape one direction or the other. Alright, so what does this look like? Here's our picture of this theoretical Turing machine. It's a big, long piece of tape. It's actually infinitely long. That's one way a Turing machine is better than a Pentium based laptop. Infinite memory, okay, unlimited tape. And there's a little read-write head here that can do two things. One, it can read a symbol directly beneath it on the tape. So the tape is broken into, you know, these little, say, 1-inch segments with a symbol in each one of these 1-inch regions. And it could be, you know, a letter or a digit or a blank or whatever your alphabet allows. And this read-write head can read the symbol under the tape. It can also write a symbol in place of the one that's already there. So, you know, magnetic tape or a fancy paper with ink or something. And this tape can move right or left. So you can turn these spindles and move everything over one spot to the right or to the left. And so our state transition rules will basically have the following form. If you're in a given state and you see a particular symbol, go to a new state, change that symbol to something else, and then move either left or right. And on a physical, you know, version of this, we would have the tape moving. But when I draw this out on paper, we're going to actually think of the read-write head as moving. Because then we can just have a string and we can move a little arrow to say which character are we sitting on top of right now. So this left or right notion is going to be a movement of the read-write head rather than the tape. So let me do an example. So our alphabet is going to consist of zeros, ones, and blanks. And our starting state is going to be S0. And here's what our set of rules looks like. If you're in state 0 and there's a 0, go to state S1, write a 1, and move to the right. If you're in S0 and there's a 1, go to state S1, write a 0, and move to the right. If you're in state S0 and there's a blank, go to state S1, write a 0, and go to the right. And so on and so forth. If you're in state S1 and there's a 0, go to state S2, write a 1, and move left. If you're in state S1 and there's a 1, go to state S1, write a 0, and move to the right. And if you're in state S1 and there's a blank, go to state S2, write a 0, and go to the left. So I have 6 rules describing the behavior of this machine. And there's one other detail. If you find a situation for which there is no matching rule, the machine halts. And that's the end of the execution. So for example, these rules here say, you know, go to state S2. And if I'm in state S2 and there's a 0 underneath my read-write head, I don't find any rule for S2, 0, machine halts, program's done. So it's possible the machine will run forever, it could just keep looping, or it could go to an undefined state, in which case it halts. So let's imagine what our tape looks like, and suppose our tape has a bunch of blanks from, you know, all the way over to the left up to some point. And then let's suppose it's got a 0 followed by a bunch of 1s followed by a bunch of 0s and then some more blanks all the way over. And let's suppose our read-write head is sitting right here to begin with. So this is a typical setup. Here's what the input tape looks like. Here's where the read-write head is sitting. Here's the list of state transitions. And S0 is our initial state. And the question is, what does this machine do? And I have no idea. I'm making this up as I go. But let's go through and pretend we're a Turing machine. So we're starting off in S0 and we have a 0 under the read-write head. So we look for a state that describes S0, 0. Hey, we're lucky. We found one right here in the very beginning. So let me make a note down here, current state. And we're starting in state S0. Okay, we've got an S0 followed by a 0. It tells me we should do the following. We should change to state S1. We should change this symbol to a 1, and we should move to the right. So we change that 0 to a 1, and we move over here to this 1 right here. We go back to the top, and we look for a rule that matches our current situation. State S1 with an input of 1. So we look for an S1, 1, S1, 1. Hey, here it is right here, S1, 1. So in this case, our new state should be S1, which is where we already are. We should change this symbol to a 0, and we should move to the right. Go back to the top. We're in state S1, and we have a 1, blah, 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 S1, 1. Stay in state S1, change this to a 0, and move to the right. Back to the top. We're in S1, we have a 1. Hey, we just saw that. Stay in state S1, change this to a 0, go to the right. Now we're in state S1 and we have a 0. So look for an S1, 0. There it is right there, S1, 0. It says change to state S2, change that 0 to a 1, move to the left, go back to the top. We're now in state S2 and we have a 0 under the read-write head. Look for an S2, 0. We don't find one. The system halts. And it's done. So what did this do? It took an input string that looked like this, 0, 1, 1, 1, 0, 0, 0, and it changed it into the following string, 1, 0, 0, 0, 1, 0, 0. Why did it do that? I don't know. Maybe it's the secret to the universe. Maybe it's just a random machine example. So every state machine, every Turing machine is described by an input tape, an initial head position, an initial state, and a set of transition rules. And you can apply these rules based on your current state and your current input symbol, and you will make changes to the tape. You'll move left or right, you'll change state, and it may just keep doing that forever and ever, or it may eventually go to an undefined state and halt. So this was Alan Turing's theoretical model of computation. This is like, you know, circa 1920s, 1930s. And people at the time were studying questions of computation, questions like, you know, are there some problems that cannot be answered? Are there limits to the kinds of things that can be computed? So very kind of foundational questions. And pretty quickly it becomes clear that, like, you need to have a rigorous notion of what it means to solve a problem. What does it mean to say an algorithm to solve a problem? And so this was a theoretical model of how you could take an algorithm and use it to systematically, you know, perform a series of steps. And so these were used to answer some fundamental questions, one of which we'll talk about on sometime next week, something called the halting problem. A question of what you can or cannot compute with a computing system. All right, so this is a basic Turing machine. And like the other systems we've been talking about today, analyzing a machine is pretty straightforward. It's tedious, but, you know, if we know the set of transition rules and we know the input tape in the initial position, we can just keep, you know, applying these rules, finding what updates should be performed, and so on and so forth. Coming up with, a set of rules to achieve some desired effect, that's harder. Programming this thing is much harder than analyzing a program. But let's do one or two. We got about 4 minutes left. Let's do one or two other Turing machines. Let's analyze them. And then on Monday we can start working on synthesis. So here's another example. There's a 3-state machine. If we're in state 0 and there's a 0, let's go to state 0, write a 1, and move to the right. If we're in state 0 and there's a 1, let's go to state 0, write a 0, and move to the right. If we're in state 0 and there's a blank, let's go to state 1, write a blank, and move to the right. Let me make this one left. So what is this going to do to an input string? We're starting in state S0 is our initial state. If we're in S0 and there's a 1, let's stay in S0. Let's write a 0 and move to the right. We're in S0 and there's a 0. Let's stay in S0. Let's write a 1 and move to the right. We're in state S0 and there's still a 0. Let's stay in S0. Write a 1, move to the right. We're in S0 and there's a 1. Let's stay in S0, write a 0, and move to the right. We're in S0 and there's a blank. Let's go to state S1, write the blank, and move to the left. And there is no state S1, so the system halts. And what did this machine do? It took an input string of 1001 and it changed it into 0110. And it left the read-write head right here. So this is a way to complement a string. Change the 1s to zeros, change the 0 to 1s. And when the machine halts, the read-write head is pointing at the least significant bit. Well, let's make one more tweak. So I'm writing this machine for a client. They want a machine that complements an input number. And let's suppose, we've got a number like this, and I want to turn this into 01101000. I want to complement it. But suppose my read-write head is not pointing on the leftmost digit to begin with. Suppose it might be pointing somewhere in the middle. Well, if I run that previous program, it's not going to change this 100. It's only going to change from this point on. So if I want to complement my entire number, the first thing I have to do is get my read-write head over this 1. And so how could I do that? Well, I could start with some state S2. And I could say if you're in state S2 and you have a 1, stay in S2, write a 1, and move left. If you're in S2 and there's a 0, stay in S2, write a 0, and move left. If you're in S2 and there's a blank, go to state S0, leave the blank there, and go to the right. And so now if I start the whole system in state S2, it's going to say I'm in S2 and there's a 1. I'll stay in S2. I'll leave this 1 intact. I'll move left. I'm in S2 and there's a 0. I'll write a 0. I'll stay in S2 and I'll move left. I'm in S2 and there's a 0. I'll stay in S2, leave the 0, and move left. I'm in S2 and there's a 1. I'll stay in S2. I'll leave the 1 and I'll move left. I'm in S2 and there's a blank. I'm going to leave the blank there. I'm going to move right. And now I'm going to go to S0. And now, if I had this part of this set of instructions as part of my program, now it's going to do my business of inverting each bit, but my read-write head is sitting right here on the left. So that's going to change all of these until it gets all the way over and then back up. So what did I do? Well, I added a function in the beginning of this program which said move all the way to the leftmost bit. And so again, we can start thinking of taking functions and putting them together and building up more complex functions. The cool part is any program that you can write in C, Java, Python, assembly language, any other language, you can write on a Turing machine. It's called computationally complete, and the benchmark when someone creates a new language is that language powerful enough to implement any algorithm you can implement on Turing machine. So this is the gold standard. You come up with a new language, people will say, is your language powerful enough to do everything that this machine can do? If it can, then you say your language is Turing complete, and people will start using it. So even though this is a really kind of clunky, sort of rudimentary seeming way to manipulate information, this is able to do anything we can do with any of our programming languages. All right, so we're a few minutes past time. Monday we will talk more about Turing machines. I'll show you some other interesting things we can do with this. We'll look at some simulators online, and then we'll talk about a very freaky kind of Turing machine called a non-deterministic Turing machine. It's a Turing machine with a friendly genie inside, and the genie helps us do computations. So we'll talk about that on Monday. All right, have a good one. I'll catch everybody next time. Thanks.
Thank you. Have a good day.
You too.